I will introduce our ICML 2023 paper, which invariance should we transfer? A Causal Minimax approach. Our poster will be presented in person on July 27. We welcome you to join us at our poster presentation to learn more about our work. Current machine learning systems, which are commonly deployed based on their in-distribution performance, often encounter the distributional shifts problem. When such shifts exist, the model may give unreliable predictions. For example, consider the system deployed to predict the FAQ score in Alzheimer's disease. During the prediction, the system can only access biomarkers of brain regions, with demographics synonymous for privacy consideration. However, changes in demographics, such as age, can cause shifts in covariates. To achieve reliability, the deployed model should be stable against demographic changes, and meanwhile to be constantly accurate across all populations. For this purpose, we aim to find the most robust, that is, minimax optimal, predictor among the set of stable predictors across all deployed environments. Our contributions are threefold. First, we attribute the distributional shifts to the mutable causal mechanisms and identify a set of stable predictors. Then, among these stable predictors, we propose to identify the most robust one. Finally, to reduce the computation cost involved, we introduce an equivalence relation and show it can reduce the complexity from NP to P. Here is the performance of our method in FAQ prediction in Alzheimer's disease. As we can see, our method significantly outperforms all baselines. How do we achieve this? Our analysis starts from the sourcing of distributional shifts. We adopt the sparse mechanism shift hypothesis, which states that distributional shifts are the results of changes in only a subset of causal mechanisms. We call this subset with the changed mechanism as the mutable set, and that with the unchanged mechanism as the stable set. In this regard, to obtain a stable predictor, we need to remove the mutable factors in x_m. To this end, we adopt interventions on the mutable variables. The intervention operation means lifting x_m from their mutable mechanisms and setting them to constant values. Thus, the intervened distribution is stable against distributional shifts. Based on this, over the derived stable distribution, we define a set of stable predictors, each corresponding to a stable subset. Then, to identify the most robust predictor, we propose to estimate the worst-case risk of each predictor. For this purpose, we derive an instrumental distribution family P_h. This family keeps the stable mechanism unchanged while allowing x_m to change arbitrarily, so as to mimic the distributional shifts in deployment. Formally, we have the following theorem, which states that the worst-case risk of each stable predictor can uniquely be identified. With this theorem, to obtain S, the naive approach is to search over all subsets of S. Is there a more efficient strategy? Indeed, we find many subsets are equivalent, in the sense that they have the same worst-case risk. Benefiting from this, we only need to search over equivalence classes. We show that these equivalence classes can be effectively recovered from the causal graph, and that this new search strategy can significantly reduce the complexity. Here is our result on synthetic data. As shown, our method can outperform all baselines. Meanwhile, the equivalence class searching significantly reduced the computational cost. To conclude, we propose a causal framework for out-of-distribution generalization. We first attribute the distributional changes to the mutable causal mechanisms. Then, based on this analysis, we identify a set of stable predictors and propose to identify the minimax optimal one among them. Finally, to reduce the computational cost involved, we propose the concept of the equivalence classes and show that it can significantly reduce the complexity. Thank you for watching. Our paper and code are available on the website. Welcome to contact us if you have any question.